In this tutorial, we will learn to define glazed elements in VOLTRA. We have adjusted the VOLTRA project from the previous tutorial by adding a double glazing panel. To better understand how glazing is defined, we zoom into the glass at a macro level. A glass pane can be subdivided into two sides so that distinct optical and thermal properties can be assigned depending on the direction of incident radiation. When radiation strikes the pane from the direction of side 1, the properties defined for side 1 such as solar reflection, solar absorption, solar transmission, and infrared emissivity are applied. If radiation approaches from side 2, the properties assigned to side 2 are considered instead. In Physibel software, the material properties defined for a color are taken from the side where radiation originates and remain active until the next boundary is reached. This means that inserting a transparent material between other transparent materials does not alter the radiation behavior. Only the properties defined for the originating side are used. So we could add any number of glass or layers between these two panes of the glass. However, if an opaque material is inserted between transparent layers, solar radiation will be absorbed and reflected within that element. For this example, we will split the outer glass into two panes so that we can define a low-E coating on the inner side of the outer glass. To visualize the model more clearly, select Y-min and zoom in on the glazing. Select the grid mesh in X direction associated with the glazing. And split it into two parts. Then select the corresponding block. And use the Copy After option. Change the copied color from 18 to 19. And adjust the X-coordinate from 2 to 3. Next, open the Colors window. Select Color 18. Copy the row information. Then select Color 19 and paste the row information. This ensures that both panes initially share identical properties. Now we define the required parameters in the Colors window. First, set the cavity between the two glass panes to transmat. Then set the cavity between the glazing panel and the wall to BC-free. This configuration enables the analysis to be performed using the radiosity method, which is explained in detail in the colors tutorials of TRISCO. It is important to note that in Physibel software, the solar transmission factor must be defined after subtracting reflection. A description of each parameter is available in the toolbar at the lower left when you select it. The Physibel online toolbox can assist with property conversion. It can be accessed through the Physibel website under Support and Toolbox. For this exercise, we use the Glass Properties Converter. The optical and thermal properties of the double glazing system can be obtained from a manufacturer's data sheet or another reliable source. In this example, we refer to the LBNL International Glazing Database. The selected double glazing unit has an air-filled cavity. For each pane, the database provides properties for side 1 and side 2. The inner side of the outer glass, which is side 2, has a low E coating. This is reflected in the emissivity value, which is significantly lower than that of side 1. The database also provides solar transmission, solar reflection, and infrared emissivity values for both sides of each pane. After entering the manufacturer data into the toolbox, the required values are calculated. In this example, the inner glass pane has identical properties on both sides, so it does not need to be subdivided in two colors. It can simply be defined as color 20. For the two sides of the outer pane, we input the side-specific properties obtained from the toolbox. Additionally, the reflection of the outer pane adjacent to a solar zone can be defined as a function of the angle of incidence of solar radiation. This can be implemented using a function, which is explained in detail in the functions tutorial. For this example, we will use a constant reflection value. It is also possible to include a PVB interlayer between the glass panes. Although this layer does not affect solar properties for the calculation in VOLTRA, it may be useful if you want to monitor its temperature. To add it, split the cell associated with color 19 again. And assign color 7 to the newly copied block using the same procedure as before. As long as the PVB layer is defined as transparent with a non-zero transmission value, it will not alter the solar analysis. If the transmission is set to 0, it becomes an opaque layer and will absorb solar radiation. To assign properties, select color 19. Copy the row. Then select color 7 and paste the row. Finally, rename color 7 as PVB layer. Next, open Report Definitions. Insert a new definition. For color 7, the PVB layer, select theta max to monitor its maximum temperature. For color 193, which represents the air cavity between the wall and the glazing panel, select theta A to track the convective temperature for the BC-free cavity. Once all parameters are defined, click Calculate to run the analysis. After the calculation is complete, open Text Output and navigate to the Results tab to review the calculated parameters. Thank you for watching, see you in the next tutorial.